Hey, it's 10 after. Perfect timing. Well, at least I feel like it's perfect timing, so that's all that matters. Okay, so hopefully your day is going well, and I would love to do a couple things, just administrative reminders and or answer some questions, and then go into questions you may have from regression so far. And there could be a lot of them, and that's good. But I do want to mention that the topic of the day today, plus the lab today, is probably the shortest little topic. Well, until we hit chapters 8 and 9, it's the least amount of time, if you will, that we're going to really need to spend on any one chapter. So the fact that chapter 3 is like one day and then all of a sudden we're having a test on it, don't worry about it. You'll see in the class today, it should be no problem at all. So let's sort of get into some administrative issues, and I want to do that by showing you my screen, and then we'll see where we get to. And if any of you had been checking Canvas recently, you might want to refresh whatever the screen is that you were utilizing for Canvas. Oh, damn it, hit the wrong button. I might disappear in a second. I think I clicked the button that said, log into a new meeting. Or so I'm not gone. Good. So in a couple things. One of them is sample exam. Yeah, the exam itself is due on Friday, but I figure tomorrow we'll be talking about that sample exam set of questions. And so if you want to ask about anything from there tomorrow, I'm thinking that's likely a good way to spend time. And so we'll be recording that as well. But I think look at that, make sure you're happy with those questions before too long. If we're looking at the material for the day today in week 2B, I just noticed right before class that what I had called week 2B there was pointing to a different page inside of a Canvas, so I had to fix that. In week 2B, there's what we're doing, which might have been included in the PDF of last time. I don't think so, but it's possible. And then if you want to look at past terms, in addition to what will be today, great. The review material tomorrow, when we record it, I'll just pop it in that location as well. And then the lab for today is GLM parameterizations, and then homework 2B is, in my opinion, pretty similar. Okay, so we should have good questions tomorrow on the sample exams, plus also those parameterizations if you'd like to ask about those things. Let me just mention one other thing, and that is about our friendly exam. I try and write a set of questions where, yes, you could answer all of the questions without even using the data set provided or the data sets provided, and without using GMT. But every so often, there are some questions which could be answered pretty efficiently utilizing GMP. Here's an example of one. If I were to ask you, okay, you did this ANOVA, what would happen if you had a larger data set size? Okay, you could say, well, in this ANOVA, we already saw statistically noticeable difference between the groups. And if I understand the theory correctly, the more data I have, the more easy it should be to spot a difference between the groups that we're comparing. So you would guess that the F ratio would be higher and the p-value would be lower. Not everyone is at that place where they'd have a guess, and their guess would be exactly right. Some people would say, okay, what I'm going to do is open up that data set that you just showed me, that we just used for the test, and I'm going to do a cut, grab the entire data set and just paste it right downstairs, effectively doubling the data set size. And then rerun the analysis. And you might notice that numbers like MSE don't change. You might notice that, yes, the degrees of freedom for error and the sums of squares for error are both approximately doubled, but MSE doesn't change because it's the ratio of two numbers which both double. You would notice that degrees of freedom between the groups, degrees of freedom due to treatment, if you will, doesn't change, but sums of squares treatment goes up. So mean square treatment would have to go up, and the F ratio would, of course, then go up. And so students who are used to using the tool can use it on the fly with either faked data sets that you can type in yourself, the numbers that you think are legit and reasonable, or using data that I provide and tweaking it to answer hypothetical questions that for some of you, the equation would answer very quickly based on glancing at it. Others of you would rather just try it out. Both approaches are absolutely fine. And so just want to mention by hand calculations. If you, when looking at the Canvas test, when you say, okay, I know what I want to write, but it's going to be a pain in the ass to typeset that because I want to use a mu and I want to use a sigma squared. That might be hard to write out. Just write it on a piece of paper. Bring some blank scratch paper to the test. Bring it to the test. Well, you're going to sit somewhere, make sure you have access to paper to write on. And later, there will be in the test the opportunity for you to upload that note sheet, not note sheet, but like that scratch paper where you did additional work. And if on question 3, part B, you think what I wrote by hand wouldn't be sufficient, but like typed into the little box inside Canvas, and you want to say, please look at my actual scratch on paper. You could again say, well, look at the page I'm uploading, and I'll give you an extra 5 minutes worth of time. And you could then upload somehow, take a picture and then somehow get it into Canvas. Just get that done, and that should be just fine. I can look elsewhere besides the test itself. So a lot of things, but I want you to sort of rest assured, should be good. And as always with any technology thing, there's going to be someone who your internet will crap out on you during the course of the test. Don't panic. Don't worry. Do a screenshot if you can. If your computer goes dead, well, that sucks. Take a picture with your phone. Let me know as soon as possible about whatever happened, and we can adjust on the fly as need be. Okay, so that's my administrative set of announcements. Any questions from y'all on administrative issues? Okay, what about questions you might have on regression? Either regression as a topic as we described it yesterday, the lab, or perhaps homework problems related to regression, a method that will be considered for your test on Thursday. Thursday to Friday, I should say, but take it on Thursday if you're ready. Get it over. Questions on regression?
When you're plotting the residuals in JMP, do you want us to do it for the X variables or the predicted variables in the X-axis?
Yeah, I don't care. That was very dismissive the way I phrased it. I saw something on TV, not TV, YouTube, well, it's the same thing, where this expert was talking about how people who are like baby boomers, when they say, I don't care, they're being dismissive. Maybe even millennials, when they say, I don't care, they're being dismissive. But people in my generation, if they say they don't care, they're saying, you do what you think is best. We're all good. I will say, in a later portion of this class, plotting the residuals on the y-axis against each of the x variables will be important to do, as well as plotting the residuals on the y-axis against the predicteds. So either way for now, you'll notice some of you, if in the TV and lifespan data from the last lab, some of you, if you plotted your residuals against the X variable, and then others plot the residuals against the predicteds, you had like a mirror image of the residual graph. but in both cases, it showed you that curvature that I was expecting you all to see. Okay, thanks for asking that question. And I think Anthony might have.
Oh yeah, it was more so about like ANOVA and not so regression. So
Sure, yeah, go for it.
so in the previous lab, there was a question mentioning what happens if we add in the treatment group where MSE is unchanged, but or yeah, what happens to the confidence intervals?
Yeah. Oh, you want me to talk about it? Sure, I can do that. Let's consider the general idea of these multiple comparisons. And I'm gonna move it over here so I can write more easily. And suppose I'm comparing three groups and doing a multiple comparisons. I guess group A, no, use a pen, get a pen. I've got groups A with 5 data points, groups B with 5 data points, group C with 5 data points. Yeah. And I might very well see, I'm going to compare A to B, A to C, and B to C. That's 3 separate comparisons that I'm doing. Yeah. Essentially, instead of 3 95% confidence intervals, we want to generate 3 confidence intervals that are closer to 97.5% confidence, which will cause the over, excuse me, no, 98% confidence intervals, which will cause the overall error rate to be closer to that target 1, 2, 3, 4, 5%. So we'll just think, go with 98% CIs. We'll get you, so that's individual, gets you 95% family level of confidence. Okay, so I'm not being precise with the numbers here, and I apologize for that, but you get the idea. Instead of doing 1, 2, 3, 95% confidence intervals, let's go with a higher level of confidence, thus lowering the error rate. So that way, overall, across all of the confidence intervals, the rate of coverage is 95% across all of them. Now, so again, 5 data points from each of the 3 groups. Now, what if we add in group D as well? Well, let's think I got A, B, A, C, A, D, B, C, B, D, and C, D levels of comparison. I've got, instead of 3 confidence intervals, I got like 6 of them, yeah? So instead of 3 98% confidence intervals, we're going to be doing 6 99.4% confidence intervals. And again, that will not perfectly match the math, but that's the idea behind the Tukey-Kremer method or the Bonferroni approach. That's going to, again, give you about that 95% overall family level of confidence. Okay, so let me ask you, if I've got a 98% confidence interval, and I'm going to 99.4% confidence intervals, wouldn't it be getting wider? The 98% one, well, to go with 99.4%, it's going to have to be a wider confidence interval, yeah? Yeah. So the individual confidence intervals will be wider. And so the difference of possible means, whether we spot that, it gets a little less likely because we're doing more comparisons. If group D effectively is a control group that you just don't care about at all, including it makes it harder to spot a difference between A and B than we earlier had. Super glad you asked that, Anthony. Did that get to your question?
Yeah, thank you.
And are you happy with the answer? Do any of you other people want to chat about this one? Okay. save that just for, oh, no. Kill. Okay, so I don't know what I just did, but you know what? I feel good. Maybe I can. Okay, done. Close, and there, I'm back, and well, whatever it is, I got this on my screen, and now I can clear it. Good, I figured it out. Okay. Any other questions on regression? Perhaps that was the most recent topic.
I have a question on the homework.
Yeah.
I'm not sure if we went over this in class, but how would you do a confidence test when you're not like the example I'm looking at is the dioecious trees where it says that slope is equal to 4. So my null hypothesis that's equal to 4, and I'm just not able to do that.
Yeah, it's a good thing that I got the software, not the software, the iPad open and running. Is in general, your test statistic T is a comparison of what you saw to what you expected to see if the null hypothesis were indeed true, divide through by some standard error. So I'm going to go with my sample slope, beta 1/2 is one notation that I could use for that. Sometimes it's called B1. But I'm going to compare it to beta 1 according to the null hypothesis and divide through by the standard error for beta 1/2. Okay, so in this case, your sample slope, which I don't know what it was, and your standard error, I don't know what it is, but you would subtract 4 there, yeah. So I don't know why I'm looking at the screen in your name, Diana, but you know. You feel okay about that?
Yes.
Okay, so we're just comparing what we saw to 4 and dividing through by the standard error, which tells me how close your estimate is to the number you're attempting to estimate. And if the number you're attempting to estimate actually is in fact really a 4, this should follow a T distribution quite nicely, no problem. If, however, the true beta 1 is something other than 4, this test statistic T will tend to be much larger than 2. I mean, it'll be further away from 0, I should say. Let's go with that. And so maybe what we could do is calculate that test statistic T. And if the value that I get for T is say 1.4, because I'm guessing here, but that's probably in the ballpark of the T value that you'll end up getting or you did get. I'm gonna say, you know what? We don't really have the ability right now to get a p-value exactly unless you use a T table. And some of you from Degrees of Freedom in that past class, you can sort of give me the exact T value or Degrees of Freedom, and you could get a p-value from that. But I'm thinking if you go with an approximate heuristic for reaching a conclusion, I'm going to know from the test statistic and then your approximate answer that you got the right idea or not. And if you remember from that past stat class, if the null hypothesis is in fact true, your test statistic T is usually in the range 2 to -2, somewhere in that range. So don't reject the null hypothesis. So don't reject the null hypothesis. But if you're out there, you reject the null hypothesis, or probably down here as well, if it's a non-directional test, again, reject the null hypothesis. So don't feel like you need to give me a p-value. I'm going to talk to the grader about this being sort of the key to the answer, and an approximate based on what your test statistic is should be fine, even if you don't have an exact p-value. So you okay with that, Diana?
Yeah, that sounds good. Is there no way to automate it on Jump, or you have to do it by hand?
No.
Okay.
Okay, I lied. There is, but not conveniently at all. And I would rather not spend class time on that. So how about we just don't?
Okay, sounds good. Thank you.
Someone else on anything regression-ish, which is a fun word to say, regression-ish. Remind me that would be a real word. Regression-like, regression-y. Okay, I'm not seeing a question, but you know what? You still have another opportunity. Okay, so what I'm going to do is dive into the topic of the day, which really is just chapter 3, which I'm even going to say is no different from ANOVA that we just looked at in chapter 2. Chapter 1, I apologize. The concept of a general linear model, and actually there's at least 3 distinct usages of the term general linear model. Our authors are using it in the most common form, okay? Anytime we can take an ANOVA or a regression problem, it is in the general linear model context. So if your response variable would be constructed as a prediction, based on like a slope times an X, or hey, you're in this group, well, here's something you add in. If I can tell you that you, excuse me, can predict your response based on something without a squaring of a variable value, or 2 variable values multiplied by each other, or some non-linear transformation, you're in the general linear model context, okay? Basically, your Y variable has to be quantitative, and your explanatory variables could be quantitative or categorical, and that's the topic of the day today. And in a later class session, both quantitative and categorical, and that's where it becomes sort of fun, okay? So I'm going to look back to the original ANOVA model we had. We said Y depends on mu for the group that you're in, plus epsilon. And epsilon tells me how far above the group mean are you. Think if you are the mouse that died at 35.5 months, and you're eating a particular diet where the average length of life is 30 months, you are living 5.5 months longer than average for your group. On the other hand, if you're eating a different diet where the average length of life is 40 months and you die at 35.5 months, you are living 4.5 months less than what I would have expected. So epsilon tells us in our ANOVA context, how far away are you from the average of the group that we're sampling from? Now we have these data points, the YIJs, and we can test hypotheses about whether all the mu's are the same, like literally mu 1, 2, 3, 4 up through mu, say 5. Are they all the same or not? We want to rephrase that now, though, to allow us to broaden our method of analysis into more complex problems. I don't want to say anymore, are the diets all the same in terms of the average length of life? I want to just fudge my words around a little bit and say, is the effect of what you eat on how long you live, is there an effect or not? Okay, so not much of a change. Is the average length of life the same across all the diets? Versus, is there an effect of what you eat on how long you live? Either no, there isn't, or yes, there is. I'm going to say, instead of writing mu I, I'm going to write mu I equals mu plus alpha I. Alpha I says that's the effect of eating this particular diet. This alpha effect might be 0, which means you're right at some number called mu. If all of the alphas are 0, if alpha 1, 2, 3, 4, 5 are all 0 in the context of perhaps the discrimination against the handicapped example. If all 5 alphas are exactly 0, mu1 equals mu2 equals mu3, 4, mu5, we could write the same thing 2 separate ways. All the groups have the same mean, or there is no effect of group on the average length of life. There is no effect. And that's nice because it broadens our ability into the future to say, well, we had a trend line perhaps, but is there an effect of which group you're in on the trend lines intersect? Or is there an effect of which group you're in on the trend line's slope? The one thing that's a bit of a wrinkle here with our concept of these alphas is if we had originally 5 group means, mu1, 2, 3, 4, 5, and now I've got alpha 1, 2, 3, 4, 5, and a mu, I've got 6 unknowns where formerly I had 5. That doesn't play so very well. We're going to have to change things up a little bit by adopting a particular style for our model. Algebraically, literally, you cannot estimate 6 parameters with only 5 means. So we could choose one of 3 styles. Actually, there's more than 3 styles, but the 3 that you'll probably, no, the 2 that you'll probably look at are inside GMP. Either the last group, and GMP will choose what group it calls the last group. And I'll show you later how you can switch which group is called the last group. You can say the last group will have an effect of 0, which means, I guess, if alpha for group 6 is group 5 is 0, that means maybe group 5 could be considered that control group, the group to which we would naturally compare. And so how different is the wheelchair group from the no handicap group? How different is the hearing loss group from the no handicap group? How different is the amputation group from the no handicap group? There's sometimes natural comparison groups, in which case that we just put that in the last slot. And the effect, if you will, alpha for that group, we're going to define it to be equal to 0. Now, that's what I first learned, and it seems quite reasonable to me. And if you do have a natural control, that's it makes a lot of sense. There is another approach, though, and that other limitation is if I require the sum of all 1, 2, 3, 4, 5 alphas to equal 0, the average effect is 0, or you could call that maybe the sum to 0 parameterization. There again are other parameterizations, but the sum to 0 parameterization is by default what JMP uses. Okay, so let me dive into that example in greater depth, unless one of you wants to ask for clarification first. Okay. So I've got these data that you've looked at already with discrimination against the handicap. So the different handicaps, none might be a natural comparison group. Yeah. It's not, however, what GMP would view as necessarily its last group. And GMP by default uses that sum to 0 parameterization. I want to look at the data. And I'm going to look at just the average of the handicap score. And I see that's wrong. Analyze distribution of the handicaps. Oh, no, I can't do that. Analyze the distribution of the scores. There we go. And let's cut that out. And analyze the distribution of the scores. Okay, good. Finally. And I'm going to sort of stack it up so that way I have the ability to remember for overall, the score, the job qualification score averages, let's just think 4.93. If I were to, however, say I want to know about the score separately, I can look at the scores separately for each of the different handicap groups. I could then find, well, I could stack them up, and I could say, well, for the amputee group, the average was only 4.43. For the crutch group, the average is 5.92. For the hearing loss group, it's 4.05. We get different means for the different groups, yeah? So I'm going to sort of like keep this guy lying around because it gives me the average across all of the groups, and that's a convenient number for the moment for me to remember. I'm going to show you how you might have done this for the lab. I'm going to fit Y by X and say handicap may help me predict the score. Click OK. And if I just show you the means and the standard deviations for each of the different groups, I get the averages. Again, the average across all the groups is 4.93, but the crutch group, the hearing loss group, no apparent handicap group, the wheelchair group, we get job qualification scores for each and every one of the categories. Yeah. Now, I'm going to move this. Can I move it partway off? I think if I move it partway off and then leave the rest there, I am. Okay, so what I'm now going to do is to show you under, instead of fit Y by X, I'm going to fit model. Okay, so starting today, we're going to use fit model a whole lot more and fit Y by X a lot less. Fit model isn't dramatically different, but it allows us to get after what I want a little bit more easily. It looks similar to before. Does the score depend on the handicap? Or perhaps, how does the score depend on the handicap? No problem. Fit model, there's still a Y. And I drag something into my X position, okay? And I'm gonna click run. Now, by default, we get actually a lot more information than you might want to see at first. And we can, oh, look, a residual graph against the predicteds, yay. I'm gonna spot my ANOVA gives the exact same results as you remember from before, boom. This effects test, that also looks just like what we had seen earlier. But I want to look at these things called parameter estimates. I'm going to open that section up. So tell me about, well, the parameter estimates. My intercept, which is sort of interesting if you think about it. We're not really saying a line, but we're still saying there's an intercept. That's a 4.93, just like what we had as the average across the groups. The intercept by default in GMP is the average across the groups, if we have only a categorical predictor. I feel more excited about this than I think any of you are looking like. And none of you use the clapping hands or other hooray emojis. I'm thinking that's really cool. Literally, I could read from this thing called intercept. Oh, that's the average across all the groups. And hold on, if you're in the amputee group, there's a negative 0.5 effect. Oh, alpha hat, we estimate the effect of amputee on the average to drop it by 0.5 of a unit. So let's say 4.93 minus 0.5, that gives me 4.43. Let's look at our averages across the different groups. So the claim is, if we were to look at the amputee group, it should be 0.5 lower than the average across all the groups, 4.93. 4.93 minus 0.5 is 4.43. Is that what I get for the amputee average? Yeah. Okay, so I'm happy about this. If it were a regular classroom, you'd see me bouncing around the front of the room. This is that cool, okay? Let's try it a little bit differently. Could we figure out what the crutch effect should be based on just the crutch average And then the average across all the groups. I'm thinking so. And something disappeared. Oh well. The average across all the groups was a 4 point. Darn it. Oh, 4.92. Good. So I got that one there. And okay. So the crutch group is here clocking at 4.921. How much above the average across all the groups is that? So I'm sorry, 5.921 minus 4.928. I'm thinking that's about a plus 1 unit above. Is the 4.921 about 1 unit above 4.93? Yeah, about so. So my guess is the crutch effect is to raise the score on average from, well, the average across all the groups to about 1 unit higher. Let's look at the estimated effect of crutches. Oh, it's to raise the average score to be about 0.993 higher than it would have been if I hadn't told you which group you're from. So far, so good? Effectively, we're getting by default, if I show you the parameter estimates inside the general linear model or fit model, we are seeing the group, the average across all the groups. And we're saying, what are the effects of amputee or crutch or hearing, or what about wheelchair? We don't have a wheelchair effect shown here. Does that mean it's 0? No. Inside GMP, they do under estimates, say show the expanded estimates, which should give you, well, a little bit more information. And let's look at that, a little additional bit of information downstairs at the bottom. We have intercept, amputee, all the way through none. Oh, look, the wheelchair effect is shown as well. So some of you might be wondering, why don't you just tell me the wheelchair effect? That's a great darn question. I think the reason is statisticians traditionally think if you have 5 groups and you tell me 4 of the 5 effects, and if the sum of the 5 effects has to be 0, the 5th effect could be calculated by simply adding up these 1, 2, 3, 4 numbers and changing the sign. So I'm going to try and do that, and I'm going to do it approximately in my head. That's a 1 minus a 0.5. That gives me 0.5 minus a 0.9. So 0.5 minus a 0.9 is a negative 0.4 minus 0. Okay, so negative 0.4 or so. Change the sign, it's a positive 0.4. Yeah, indeed, you can, from the first 4 effects, find that 5th for free. Again, this is where I get excited in the front of the room and bounce around. There's something different about these virtual classes, though. Okay. I'm thinking this is sort of cool. But if you want to have a comparison to the last group, we don't really have that here. We have just the average across all the groups and the effect of each of the 1, 2, 3, 4, 5 groups on that average. There is another approach, and it by JMP is for fun, for free. Under estimates, tell me the indicator parameterization. Yeah, use a reference group is how I phrase it. Show me the indicator parameterization estimates. I'm going to turn those on downstairs, and I'm going to say, aha, the intercept, and maybe I'll get rid of that one. And this one, and this one, so we can look at our indicator parameterization estimates. The intercept is 5.34. Well, hold on. 5.34. Oh, we saw that as the wheelchair group. The last group becomes our intercept group. The group that is not appearing here is the group with an alpha of 0 That is the group that defines the mean mu. If you will, amputee, crutch here, and wheelchair. None. The wheelchair group is the intercept average. And compared to wheelchair, let's do a little bit of quick math and say amputees are how much different from wheelchair. This says about 0.91 below. Let's look at the wheelchair of 5.34 and the amputee 4.23. Yes, that is about a 0.9 difference. So with this indicator parameterization, we're saying one of your groups gets you your mu, and the effects or the differences between each of the other groups and the reference group, those define your effects. And the regular classroom, what I tend to do at this point in time in the term is say, doesn't it just depend on where you're at? And I call on someone who's like 6 foot or 6'2" and say, hey, could you stand up, please? And they surely do. And then they look at me and I look at them and they say, how much shorter than you am I? And they say, well, if they're 6'2", they say, you're about 4, 5, maybe 6 inches shorter than me. Okay, so we're good. I'm 6 inches shorter than that guy that's 6'2". Then I ask another student who's on the shorter end, who's about 5'3", how different am I? And they say, oh, well, you're about 5 inches taller than I am. And then we look around the room, and could each student in the room compare their height to the tall guy and the short guy? How different would each of those heights be from the tall guy's height and the short person's height? I could calculate those differences, and if I kept track of sign because of greater than and less than, I know where everyone's height is based on the height of the reference person, and also the differences in everyone's height from that reference student. Indicator of parameterization. The person I'm comparing to is that intercept height. What about this other approach, where the intercept is from this sum to zero parameterization? Well, if it's a small enough class, I can ask for all the students' heights, and sometimes I do that earlier in the term, and find the average height. And I then compare my height to the average. And then I can compare every student's height to that average height. Is everyone a difference from the average? Maybe that difference is zero, but does everyone have how much taller than average are you? Yeah. So normal estimates from GMT compared to average. Indicator compared to a reference, and the reference is that intercept. But in the sum to zero parameterization, the intercept is the average across all of them. So that's the basic idea behind general linear models. And we're going to, I'm going to talk about that in the future, and that'll be next week, because I want you to focus on making sure you get this last bit down. And I would claim this parameterization is not too difficult. But you know what? There's a lab on it today. There's a homework assignment today. Yeah, it's due on Monday. But if you do it today, you can ask questions about it, just like about the lab in class tomorrow before taking your test. Okay, so looks like we got 6 extra minutes, because I misestimated how many questions you'd have on regression. Any questions on absolutely anything, though? Because I've got time. Another 5.5 minutes. And hopefully I have more time than that, but
Can you kind of re-go over why the in the parameterization, why the wheelchair became the intercept, the mean for that?
Yeah, it's because it's the last group. And a great question, because it allows me to remember, I wanted to show you how to take one of the other groups and turn it into that reference group. And I think none as a reference group makes a lot of sense, yeah? Yeah. So if I take that column, I right-click at the header, And then under column properties, I'm going to say, take the values in this column and put them in my choice of order, not whatever JMP chose or the person who created the data set might have chosen. In JMP, for each column of categorical values, if it's like categorical, like nominal, there is a natural order, and we could, under column properties, choose that order under column properties value order. Okay, so I see the options here are, well, handicap. I'm going to have alphabetically A comes first. That will be my first group. Crutch, hearing, none, wheelchair. Wheelchair in that last slot is either the reference group with the indicator parameterizations or the one that doesn't show up at all until you say you want the expanded parameter estimate. I could take my none and slide it into that last slot, which makes sense to me. Click OK. Redo my analysis under Analyze, fit Y by X. I'm going to say, oh, I'm sorry, under Analyze Fit Model, that's what we're doing now. It applies to Fit Y by X as well, but Fit Model is the method we want to use now. Recall is your friend. I'm going to click Recall Score Defense. Well, yeah, that's still what I want to do. So if you ever want to do a shortcut, Recall will probably get you to about where you want to be. I'm going to run that analysis again. Lots of stuff. I don't need to see most of it, but I'm interested now in our friendly parameter estimates. And I still see here our 4.92 for our average. Yeah. And amputee. Oh, but wheelchair is showing. Again, sum to 0 with some of these 1, 2, 3, 4 separate effects on the average, the effect of amputee on the average, the effect of hearing loss on the average. The sum of these 4, then switch the sign to get the none effect. But if you were to prefer the indicator parameterization, and that's what I think your question, Kendall, was about, I could say, okay, the intercept is now the reference group's average. But if you are in the amputee group, you go down by 0.47. If you're in the crunch group, you go up by 1.02. So we're now comparing to 4.9 instead of comparing to what we earlier were comparing to, the wheelchair group's average. We're now comparing to the none average, the natural reference group in this experiment. So Kendall, I think I might have answered your question, but I don't know, did I?
Yeah, thank you.
Cool. Okay. Other questions?
I had a question for the lab.
Yeah.
In order to tell the non-constant variance, is it from the residual graph or the residual graph versus predicted graph? Or not neither?
When you say residual graph, I think residual versus predicted, residual versus the explanatory variable X, or residual versus the categorical predictor, like in the ANOVA context, or just not even versus anything, but rather a histogram of the residuals.
Okay.
It's the first 3, not the 4.
Okay, sounds good. Thank you.
The histogram of the residuals doesn't help me spot where the variance is equal across the situations. The residuals plotted against each of the X's, if you see a funnel shape, that's bad. If you see what looks like a football shape or like a box shape, not a banana, you're in good shape. Banana is curvature. Funnel shape is lack of equality of spread. Box and football are A-okay.
Okay, thank you.
To follow up on that, normality would be the histogram, right?
Yes.
Okay. Good.
The histogram and then Shapiro-Wilks.
Yeah. Okay, thank you.
Whereas for the non-constant variance, if you had categorical explanatory variables, use Levine. If you've got a quantitative explanatory variable, There is an approach towards looking for non-constant variance in a more algorithmic fashion, but that's not one we're going into this term, and usually I don't. In a 15-week term, and most of you will have graduated before we have semesters here, but you know what I mean? We would have an extra few class sessions and be able to get to it there. Okay, what I'm going to do is stop the share and stop the recording if there are no additional questions. And then I'm going to say the lab itself on this topic really gets a bunch of good questions. I'm going to say one thing to be careful about is the average of the two averages, the M's and the F's in the dioecious trees. Yeah, that's helpful. That is not, however, the grand mean. The average of the averages is not the average across all the data points necessarily, unless each group has the same sample size. And the average of the averages, which is typically not something we care too much about, really matters a lot in this lab. So if it says the average of the averages, calculate it that way. Don't just go with the average of all the data points. That is your hint. But there will be good questions tomorrow. I'll see you then. Bye.